go ahead. I'll start the share. Um, how's that, Nicole? Can you see the full
Looks great.
slide? Great. Well, thank you so much. Thank you so much, Nicole, and everyone for joining. It's a pleasure to be talking to you all today. And I'm going to be talking to you about what is just such a huge topic, planetary habitability. And as you can see, the title is Understanding It. And the reason I call that is because that's what I do. I try and understand planetary habitability. I've published a lot of scientific papers, written a few books on this topic. And I'm just going to skim across the surface of a couple of features of planetary habitability today that I'm certainly willing to answer any questions during the question time and afterwards. Feel free to reach out to me. I'll be happy to hear any questions or thoughts that you might have. And I'm showing on this first slide the three main terrestrial planets from our planetary system from which we learn about planetary habitability: Venus, Earth, and of course Mars. The reason that I'm including them and not Mercury is because, as you're going to see, a lot of it is to do with the atmosphere. If I were to include another object here from our solar system, it would undoubtedly be Titan, one of Saturn's moons that has an atmospheric pressure at the surface that is even more than Earth, about 50% more, in fact. So I will mention that in case you're wondering about my background, this is kind of what it might look like on the surface of Venus. Venus is, along with Mars, two planets that I study very closely in comparison with Earth, and what that teaches about why Earth is habitable and how it has maintained that over a long period of time. So let's get right into it. Now, first of all, we need to ask the question, what is planetary habitability? As I said, this is an extremely large topic with many facets to it. And as I said, I'll just be talking you through a couple of features of planetary habitability today. But we can talk about planetary habitability in multiple ways, but fundamentally the way I think of it is it's all about the energy balance. And the energy balance at the, sorry, just moving the little, my talking head out of the way here so I can see the text on my screen. Energy balance at the surface of the planet, because that is essentially what's driving the evolution of the surface conditions. So when we're talking about planetary habitability, we think about, well, what is it that's making the planet habitable, and which of those features of the planet are dominating? And what measurements do we need to make? And what can we do with those measurements in trying to understand more about how that planet has remained habitable over a long period of time? And ultimately, what we're trying to do is create a model for planetary habitability that will allow us to apply that model to planets outside of our solar system, exoplanets, for which we know far less about those planets than we do for the planets in our solar system. And I mentioned at the bottom the entropic bias. That's something that we always need to be cognizant of, because we're usually talking about Earth as a template for a habitable planet, but there's a lot of features of Earth which some may be fairly specific to Earth, but some which may not be. But we need to be careful about attributing too much to specific features of Earth, and that comes back to which factors are dominating. So now it is the summertime, and I recently just finished teaching classes here at UC Riverside. We're on the quarter system, and so our academic year doesn't finish until the beginning of June. And the summertime means that I can engage in some of my less scientific pursuits, one of which is board games, and I love Terraforming Mars. It's one of my favorite games. And for those of you who are not familiar, the game Terraforming Mars is really about changing three primary properties of Mars, which is the atmosphere, the temperature, and adding surface liquid water. And you go through this game playing different cards, different technology cards, trying to put surface liquid water on Mars in order to terraform it and essentially make it habitable. So why is surface liquid water such an important part of this discussion when we're talking about planetary habitability? And this is something that we often come back to, this property of Earth, whereby we have 70% of the Earth's surface is covered in liquid water. Is that important? Well, this is something that I would argue is actually very, very important. And as I said, we try not to be too anthropic about this and try to be cognizant of the biases that we're bringing to the table here. But there are a number of reasons why we might say that surface liquid water is incredibly important. For example, water, which consists of hydrogen and oxygen, those independently are extremely common, and the molecular version of those, H2O, that is extremely common. We see that within our solar system, certainly in the outer parts of our planetary system, but also beyond the solar system as well. Water is everywhere. Secondly, water is a neutral solvent in which you can have chemistry happening that will enable biology. And that is one of the main reasons why water has been so important for Earth's biology history. And you can imagine that there certainly are other alternatives to water that would serve the same purpose. However, one of the incredible things about water is that it is in a liquid state at reasonably high temperatures. Many of the alternatives, those are in a liquid state at much lower temperatures. And so any chemistry that's happening will happen at a much slower rate. And so planetary habitability, you can think of as the ability of a planet to retain surface liquid water. And there's a couple of important pieces to that. One is that if it's water on the surface, then it requires the presence of an atmosphere, because what you really need is a temperature range. And this is where the energy budget part comes into play, because if you are requiring surface liquid water at, say, around about 1 bar atmosphere pressure, then it means that the temperature range is going to be between 0 and 100 degrees Celsius. Now we can quantify it. Instead of just talking about it in some fluffy qualitative sense, we can say, okay, now we have some numbers, and we can calculate the energy budget for the planet, and in particular the atmosphere, the radiation of the surface, that would allow that temperature range to be maintained over long periods of time. And this is incredibly important for exoplanets, where we are not going to be able to go there anytime soon. And so that's an incredibly important part of that discussion, because we need to keep in mind that those limitations. So having surface liquid water is very, very complicated, because it depends on many, many things. This is a diagram which is colloquially referred to as planets are hard. And it's intended to kind of intimidate in a way, to give you a sense for all the many different features which would allow for the presence of surface liquid water. And so there's three main categories which are shown here. And the three categories are the properties of the star, which is shown up in the top left, the properties of the planetary system, and of course the properties of the planet itself. And what I'm going to do for the remainder of this presentation is I'm going to briefly mention a few aspects from all three of these categories as I said, to give you a sense for the kinds of things you might want to think about if you're imagining a planet or studying a planet where you're trying to assess the long-term planetary habitability of that planet. So first of all, we're going to start with the star. Now, as I mentioned, the planetary habitability is really about assessing the energy budget, and by far the overwhelming source of energy for a typical planet is the star that it's orbiting. That is providing an enormous amount of energy at the top of the atmosphere and then warming the planet up, and the planet is re-radiating that energy. And there are all different kinds of stars. We see them as represented as different colors, which is an indication of temperature. They're all different kinds of luminosities, meaning power output. But we can look at all different kinds of stars in a pretty interesting way. And what I'm going to show you now is an animation which hopefully works well on Zoom, whereby we're going to take these stars, which you can see in this image, and we're going to divide them up. And we are going to divide them up, first of all, by color. We're going to move the blue stars over to the left, and then we're going to move the red stars over to the right. Then we're going to divide them by brightness. The brighter stars will move to the top, and the fainter stars will move to the bottom. And this is a diagram which we refer to as the Hertzsprung-Russell diagram, because it shows the lifetimes of stars depending on their size. And what's indicated there is the main sequence where stars are burning hydrogen, and here is where our sun lies. It's kind of this middle average kind of a star. Now, the point here is that the habitability of your planet can really depend a lot on the kind of star, because our sun, for example, has a lifetime on the main sequence of about 10 billion years, and we're about halfway through that. Now, up in the top left, we have these blue massive stars. Now, they have an incredible energy output, which may seem good for planetary habitability. However, they don't live very long, whereas our sun will live for about 10 billion years on the main sequence. Those blue stars will typically only live for about 10 million years, and then they explode in a supernova, and that, of course, would be devastating. On the other hand, if we look down at the bottom right, we have small stars, often called red dwarf stars, and red dwarf stars, they can live a very long time, much longer than our sun. However, they are also very, very active. They have a lot of flares, they have a lot of spots on the surface of the star, and that can affect the atmospheres of the stars in a very profound way, as I'm going to show you in a moment. So all of this to say that the kind of star that the planet is orbiting matters. It matters about how long it lives. It matters about how active the star is. But there are many other features of the star that will determine what the surface of your planet is going to be like. Now, I want to talk a little bit about the planetary system. And there are a lot of features with the planetary system that are going to affect planetary habitability. But one of those is what other kinds of planets that are there and what remains of the building blocks of planets exist within that system. By the way, Nicole, is that animation rendering okay? Can you see it?
Yes, yes.
Excellent, good. I always worry a little bit about that with Zoom. This is showing the asteroids within our solar system, and you can see it's highlighting different kinds of asteroids, and you can see the orbits going all the way out to Mars there. And the asteroids have had, as well as being leftovers of the building blocks of planets, they can also have ongoing effects with impacts on the surfaces of planets, and Mars has certainly been no stranger to that. But also, as we're continuing to zoom out, you can see that there lies Jupiter. And Jupiter has had an incredibly strong impact on the development of Mars through time, both in the formation of Mars, which we'll come back to in a moment, but also in scattering asteroids throughout the solar system. And that is a double-edged sword. Having a giant planet like Jupiter has an incredible effect on the development of habitable planets within the system. So what do I mean by that? Well, as you know, we have 4 giant planets within our planetary system: Jupiter, Saturn, Uranus, and Neptune. And I don't know if you've ever thought about the effect or the role that these planets may have had on the development of life on Earth. But it's something that we really should think about. And the reason is because we now know from other planetary systems that our system is quite unusual, because other planetary systems, we have surveyed them long enough to know that giant planets like Jupiter, Saturn, Uranus, Neptune, that are far from their stars, are quite rare, and rare at about the 10% level. And so that means that if Jupiter has had an effect of habitability, then that could be really important, since most other planetary systems do not have that kind of planet. So there's several ways in which Jupiter has affected planetary habitability, and one of those is impacts. And Jupiter has scattered water throughout the planetary system, and that means that many of the impacts that have occurred on Earth and on Mars and on Venus have been the result of Jupiter scattering water throughout the solar system. So that's a good thing when it happens early in providing the surface water for those planets. On the other hand, as the planet evolves, you tend to like impacts less and less. Certainly, we can ask the dinosaurs what they thought about that. But you can see here in this picture, this is a case where Jupiter absorbed an impact. This occurred back in, I believe it was 1994. Comet Shoemaker-Levy 9 hit Jupiter, and the fairly young at that point Hubble Space Telescope took some extraordinary images of that. And this was a comet that was in an Earth-crossing orbit. It didn't hit Earth. Instead hit Jupiter. And so you can have a giant planet scattering water to the inner part of the system early in their history, and you can also have it absorbing impacts later in the history. And for this reason, many people have argued that having giant planets may actually be a very important component in the development of planetary habitability. So, finally, let's talk about the planet itself. And of course, we're going to compare Earth and Mars. Mars is significantly smaller than Earth. It's about half the size, but it's only about 1/10 of the mass. And the reasons for that are many, but the development of formation scenarios for our solar system have shown that, once again, Jupiter has played a major role in that. Jupiter is about 5 astronomical units away from the sun presently, but during the early stages, it moved around a lot, and that was mostly prior to the formation of the terrestrial planets. But it undoubtedly did truncate the size of Mars during formation, meaning that Mars likely would have been a lot larger had Jupiter not been there. Now, this has had numerous consequences for Mars, and one of the ways in which we see this is the atmosphere. Now, the atmosphere of Mars is very, very modest compared with Earth. It's less than 1% of the mass of Earth's atmosphere. And one of the ways in which we can diagnose what has happened with the Martian atmosphere through time is by looking at the composition. As you may know, the atmosphere of Mars is mostly carbon dioxide, but there are a few other interesting elements as well, and most particularly argon. You can see shown on the left, there's a breakdown of that composition, And argon is incredibly useful because it allows us to track the loss of the Martian atmosphere through time. There are various isotopes of argon, and which means that you have an argon atom with different numbers of neutrons, same number of protons, of course, but different number of neutrons in the atom. And the lighter versions of argon tend to float at the top of the atmosphere, and they are more easily removed. And so when we compare these different isotopes, we are able to track the loss of the Martian atmosphere. And a spacecraft which has been doing this is called the MAVEN spacecraft. And this is an animation that was produced by the MAVEN team, which is showing the effect of the solar wind hitting the Martian atmosphere. And this is a computer model which is showing what we expect to see from the loss of atoms from the Martian atmosphere. And what you're going to see in a moment is the actual data, which matches very well with the model. And from this, we can diagnose the lost rates of the Martian atmosphere and what that could mean for what the Martian atmosphere may have looked like in the past, and allows us to constrain the very early period of Martian history when indeed it almost certainly did have surface liquid water. So Mars, at one point, was a habitable planet according to that definition, but the loss of the atmosphere has made it very difficult for water to be in a liquid state on the surface. And so the small size of Mars, the loss of the atmosphere, has had a profound effect on its habitability. Once again, that loss, not just depending on the size of the planet, but also the type of star that it's orbiting, because if it's a smaller star, then it would have lost its atmosphere even quicker because of the activity. So why is all of this important? As I mentioned at the beginning, we're trying to create models, and the models are being applied to planets around other stars, exoplanets. And one thing that we learned from the NASA Kepler mission is that the occurrence rate of planets increases to smaller sizes. That means small planets are far more common than larger planets. And you're seeing here a gallery of planets which have been discovered by Kepler, all the way from Kepler 22b on the left, which is twice the size of Earth, all the way down to Earth. But the occurrence rate increases beyond Earth. And what that means is Mars-sized planets are even more common than Earth-sized planets. So there's a lot of Mars-sized planets out there, and creating these models that will allow us to assess the habitability of planets that are between the size of Mars and Earth through time is a critical piece of this. And this, of course, leads into the follow-up characterization that we're trying to do right now with the James Webb Space Telescope, but also with future planned facilities, where we are measuring the atmospheres of these exoplanets to look for signs of habitability. And one of the key things you'll note right down the bottom there is it says water vapor suggests habitability. Water vapor being present in the atmosphere can be a sign that you're seeing evaporation from perhaps a water-dominated surface. And you can even have planets where there are no continents. They are water worlds where you have far more water inventory than the Earth presently has. So I want to make sure I allow enough time for questions. So I'm just going to end with a list of questions which you can think about, and you can see that many of them are extremely relevant to Mars. One of the early ones, did Mars have surface water? It certainly did earlier on in its history, but then you can see the fifth question there, how small can a planet be and remain habitable? And that's one of the key things which Mars teaches us about. And there's a lot of other features in there which we care about for Mars, such as the dependence of atmospheric erosion on magnetic fields, which is still an active area of research. So with that, I'll open up for questions, and happy to talk with you all more about this.
Thank you. Wonderful, clear, concise presentation, Professor Kane. If you have a question, you can raise your Zoom hand. If I cannot hear you, the case same as yesterday, I couldn't hear certain people. Please type your question in the chat. We only have a few minutes before Dr. McKay is scheduled to arrive. All right, first question being Juan. Unmute yourself, please.
Yeah, hi. So I was wondering if you have any idea, recently SpaceX talked about their Starship and how they were developing their heat shield, but they were talking about how because of the composition of the Martian atmosphere, it was very difficult to design heat shields in terms of like something around like oxygen fires or like because of the Martian atmosphere and it being so much of carbon dioxide, the flames and the conditions generated on the heat shield were really problematic for them.
Right. I don't know a lot about the effect of the Martian atmosphere on heat shields, other than the deployment of things like the Perseverance rover, where it, it the difficulty that I've seen with the heat shields, when you compare, say, Mars and Earth, is that for when you're saying having re-entry into Earth's atmosphere, you have to deploy the heat shield quite earlier on. Whereas Mars, you deploy that heat shield as late as possible, because as you're heading towards the Martian surface, there just isn't enough atmosphere for that to be important. And so the late deployment of the heat shield and then injection of the heat shield before landing the rover, I know, was a significant challenge in those cases. But interesting points about the effect of flames on the heat shield regarding the composition. I'll look more into that. That's really interesting.
Thank
Great,
you.
great question. Jad?
Good evening, ma'am. I have a small question about the main role of the Goldilocks zone that the Earth locates in. What about the main role of the Goldilocks zone? Because we can't make the water liquid, or it become liquid only in the Goldilocks zone and suitable temperature. So how about that?
So are you question? Oh, sorry. Are you asking about the boundaries of the habitable zone?
I'm asking about the Goldilocks zone.
Yes. Right. What is your question about the Goldilocks zone?
Doesn't it play a major role in detecting the temperature that the planet should have for offering water, liquid
Yeah.
water?
Yes. And thank you for bringing this up. I mean, obviously with limited time, I didn't really have a lot of time to talk about the habitable zone. As you said, it's sometimes called the Goldilocks zone. That is a set of distances from the star where you can have water in a liquid state on the surface. And that's a key part of this, because there's a lot of water in the outer part of our solar system, and some of it is in a liquid state, but that water is under the ice of moons like Europa and Enceladus. And so I have this discussion with colleagues sometimes when they say, well, when you talk about the habitable zone, why aren't you including the outer parts of the solar system? And that's because you have to have an atmosphere in order to use the habitable zone. And when I say use it, I mean use it for other planetary systems, because other planetary systems, it's all about measuring the atmosphere to diagnose surface liquid water. And so the purpose of the Goldilocks zone is for remote sensing for exoplanetary systems, not for icy moons within our solar system, because we already know that those moons have subsurface water, and we will never know that for another planetary system. So yeah, thanks for bringing that up. Hubble zone is an important part of this discussion.
Wonderful. Dr. McKay has joined. I think we have time for one more question. Karun, please ask your question quickly. Everything else we can address at the end of the call.
Hi, ma'am. I just had a quick question. My question was, once we reach Mars, how do we plan to terraform the atmosphere? Like, what steps are we going to take or would take to terraform the atmosphere so that one day we can walk around Mars without oxygen tanks?
So I teach a class called Planets in Science Fiction where we talk about terraforming Mars a lot. And one of the things about terraforming Mars is that there are some things that you could change, but some things that you cannot. So solving the issue of, say, the atmospheric pressure is a very, very difficult one because having that produced by the planet itself is going to be very hard because you have to essentially degas enough of that composition from the interior of the planet, which is very difficult to do when it's so small and so old. So you'd need to add that some other way. But here's the thing: if you were able to add that atmosphere, there are some things about Mars that you cannot terraform. For example, it is a tenth of Earth's mass. That isn't changing. And so that means you will always have that 38% surface gravity. That is not a terraformable feature. And so that low surface gravity combined with the radiation from the sun means that whatever atmosphere that you add, you will lose it again. And so you'd need to find some other way to mitigate that. So there's a lot of things to think about when terraforming Mars, but it's worth keeping in mind that there are some features of the planet that are unchangeable, and you would have to work around that to create long-term sustainability.
Thank you so much, Professor Kane. We can get to more questions at the end of the talk, but to be respectful to Dr. McKay's time and everyone else's, I would like to introduce Dr. Chris McKay, who is a renowned planetary scientist and astrobiologist at NASA Ames Research Center, specializing in planetary atmospheres, astrobiology, and terraforming. Welcome, Dr. McKay. I'm so happy you're here.
Great. Hi, Nicole. I'm going to share screen. Is that okay? So
Yeah, of course.
How to share screen. Share window. Let's see if I can share this. Well, what do you see?
Just the square still, just the people. You have permission to share screen. Sometimes
Okay.
you have to click one of your own
Okay.
mini screens. They
Gotcha.
update it. They update it all the time.
Safari.
Or you can send me your presentation and I can.
Okay. Story reactions. Just a second. I'm not figuring out how to share the window. Let me just close the.
Oh, here it is. Here it is. Account any Connect VPN is what I see.
Yeah, that's not what I want to share, though. Of course. Your screen sharing. Okay, let's see what it says. I'm going to stop sharing and try again.
Okay.
Um,
Or email. Oh, something's. Oh,
okay,
there it is.
Okay.
Life detection on Mars.
Yeah, I can't share the window, a
That's
particular
all right.
window, so I'm just sharing screen.
Perfect.
Okay, so I can't, when I'm doing this, I can't see you guys. Actually, maybe, let's see if I can do it. Well, let me try it this way. Can you still see life detection on Mars?
Yeah. Yeah.
Okay. All right. Good morning, everyone. It's morning here. What I wanted to do was talk about a particularly interesting aspect of designing a Mars mission, a Mars base, or a human mission, which is my understanding of what you guys are trying to do, which is the question of life, Mars life, and the need for life detection. I'm going to try to make the case to convince you today that you need to include life detection in what you're planning to do. So when you're planning a base on Mars, if you're planning missions to Mars, if you're planning to put humans on Mars, you need to include life detection. And I'm going to explain why I think that's the case. Okay, first, the governing rules are what's called the Outer Space Treaty. I'm not going to go into detail on this, except to say that the Outer Space Treaty requires that you do not harm the Earth by bringing back anything from space. Kind of common sense. And in the United States, at least, the Outer Space Treaty, the United States is a signatory to the Outer Space Treaty, and that has the force of federal law on all U.S. entities, including private space companies. So suppose there was a private space company, Space Z, that was going to go to Mars and do stuff. It is required to comply with the Outer Space Treaty, even if it receives no federal funding, even if it's completely funded by the Space Z company itself. Okay, so that's an important point, which means that the rules that I'm going to be talking about return from Mars, apply to all U.S. entities. And I believe it's the same situation in other countries where all entities are subject, all signatory countries, and most countries are signatories to the Outer Space Treaty. So the question is there life on Mars? Can we assume that the answer is no? Most people that are planning missions to Mars assume that the answer for life on Mars is no. So let's look at that. The relevant data are the Viking biology experiments, the Phoenix discovery of perchlorate, and the current missions which have detected low levels of organics. Based on this, I'll summarize and I'll go into a little more detail. Most Mars scientists, myself included, contend that what we've seen on Mars, the reactivity in the soil, is chemical and there is no surface biology now. We just did a recent paper that summarized the Viking biology experiments making this case. But this is not unanimous. For example, Gil Levin, to his death a few years ago, believed that his instrument, the LR experiment, did detect life on Mars. And there's other scientists, various levels of credibility, from world-class scientists down to just science fiction writers, who like to think about the Viking results indicating that there was life. So both NASA and COSPAR, the official committee that implements the Outer Space Treaty, consider any sample from return to Mars as a potential risk. I do too, although I am of the view that there is no scientific evidence for life on Mars now on the surface, and that the evidence points the other way. I think that the precautionary principle requires that we treat it as a potential risk. So conclusion is, it is unlikely that public opinion or legal procedures will support the assumption of no life on Mars for the purposes of astronaut return to Earth without further analyses on Mars, without due diligence in confirming that there's no life before the astronauts or the samples come back. And when I emphasize legal procedures here, because when it comes to returning samples to Earth, virtually all citizens of the United States would have legal standing in a lawsuit to prevent the return to Earth and the potential contamination of the Earth. So it's not a trivial issue that it may be a legal issue, not a science issue. So let's just quickly review. 1976, almost 50 years ago, Viking lands on Mars, has 3 biology experiments, so far the only biology experiments ever sent anywhere else, and a gas chromatograph mass spectrometer to detect organics. Okay, that mission 50 years ago is still the focus of the argument about life on Mars. The 3 biology experiments basically took samples, put them in chambers, added soup, added carbon labeled soup or nutrient labeled soup, or added water and turned on a light. Basically, they tried to incubate the sample. They tried to grow any microbes in the sample. The idea is that if there was life in the sample and we gave it soup, it would eat the soup. That's an interesting assumption, but we now know that that doesn't work very well, even here on Earth. Remember, these experiments were done 50 years ago. They were designed 60 years ago. That was the best they could do. The only way to do microbiology 60 years ago was to try to grow it in a culture. That's what Viking tried to do. But growth experiments presuppose a knowledge of the conditions and nutrients needed for growth. And we now know that 90% or more of the bacteria in your backyard cannot be grown in any culture medium. Non-cultural, not culturing is an extremely limited technique. So we don't do life detection that anyway. Now, our plans for life detection are not based on growing microbes. They're based on detecting molecules, DNA, amino acids, lipids, from which life is made. So we detect the bricks that life is made out of, not the ability of life to eat food. And that's an important conceptual departure from Viking. So what were the results from Viking? Viking found that the soil was active. It released oxygen when it was wetted. It did, in one of the experiments, the soup was consumed, but no organics were found in the sample at very, very low levels, which surprised everybody. How could you have life with no organics? That was the Viking mystery. That mystery persisted until Phoenix 2008. Phoenix 2008 produced an incredible discovery on Mars. The implications for human exploration are profound, and you probably don't know about it. And that is the discovery not of ice, which is what Phoenix was sent to investigate. That was well known, and it's still well known, but perchlorate. Phoenix found the soil, pH 8, okay, carbonates, okay, segregated ice, K, no organics, the instruments failed, but it did succeed in discovering that the Martian soil contains about 0.5 weight percent of perchlorate. That is a stunning result and has important implications for your work designing a Mars mission, designing a Mars base. Perchlorate is the most oxidized form of chlorine. It's a chlorine atom connected to 4 oxygen atoms. It is the most oxidized. It's very rare on Earth and highly regulated by the EPA because it's toxic to humans. It causes thyroid conditions. It's regulated in the US in groundwater at parts per billion level. But it's also used in rocket fuel. Perchlorates, when heated up, perchlorate is very stable at room temperature, but when heated up, it decomposes and releases hot oxygen atoms, which is why it's used in rocket fuel. If any of you are model rocketers and launch rockets, small home rockets, you will be familiar with perchlorate. It's also is used in the shuttle solid rocket boosters. It's also a very good antifreeze. If it wasn't toxic, we would put it on the roads in the winter. It's also edible by certain microorganisms. Certain microorganisms can use perchlorate the way humans use oxygen as an oxidizer, as a terminal electron acceptor. So these are interesting facts. They're important facts because perchlorate is present on Mars at very high concentrations. Well, looking back at the Viking results, perchlorate changes our interpretation completely. Now, I submit we understand the Viking results. We understand them because of perchlorate. Viking did not detect organics due to the confounding effects of perchlorate on the GCMS. When the sample in the GCMS was heated up, the perchlorate decomposed. The hot reaction out of oxygen atoms from the perchlorate destroyed the organics they were trying to detect. And the radiolysis, cosmic ray breakdown of perchlorate explains the oxygen released by the other instruments and the consumption of organics by the other instruments. In my mind, and in this recent paper, we contend that the perchlorate discovery provides the most straightforward explanation for all the Viking results, and there is no need to postulate life forms on Mars to account for the Viking results. So that's our key conclusion. There is no need to postulate life forms on Mars to account for the Viking results. Now, that does not mean that the Viking results prove there's no life. It just means that the Viking results do not prove there is life. The distinction is critical And in a court of law, it's fundamental, right? If you're going to say, I'm going to bring my astronauts back from Mars because Vikings showed there's no life on Mars, that doesn't hold up. Even anti-lifers, so to speak, like myself, say that that's wrong. What Viking showed is that its results do not tell us about life. There's no need to postulate life on Mars. Perchlorate provides the explanation. So let's now think about a mission to Mars. It means that you need to plan, your team, as you prepare your mission, as you think about your base, you need to plan on in situ life detection. You need a tricorder. You need Mr. Spock and a tricorder to search for life for two reasons, I would argue. One is for compliance with the Outer Space Treaty. If you want to send your astronauts home, that's a return. That's a sample return. That's a return to Earth. That is governed by the Outer Space Treaty. And you have to show that you've done due diligence to confirm that your astronauts are not bringing back something that's alive from Mars, right? And I'll talk about how you would do that. How would you do due diligence, not absolute proof. In science, there's no such thing as absolute proof, but there is such thing as due diligence. You do the best you can to show what you're trying to do. And that's the standard, a reasonable standard in legal proceedings as well. We propose you do it with a payload that we've proposed before, icebreaker mission. The instrument suite would be a GCMS, a microcapillary electrophoresis to detect amino acids, a wet chemistry system, just like on Phoenix, and a amino acid detector that detects small molecules. A lack of result, the null result, which is what you'd have to show, would be the detection of amino acids and lipids, yes, but only as expected from meteoritic input. So if you were to show that you were able to analyze the soil where the astronauts landed, and it had amino acids and lipids, that shows your instruments work. But the amino acids and lipids you see are not biological. They are from meteorites. You've done what I would consider due diligence, and I would testify in a court that that is an adequate life detection for astronaut return and demonstrated compliance with the Outer Space Treaty. Here is what I mean by meteoritic, not biological. Biology uses amino acids. Meteorites have amino acids, but they're different. I'm not going to go into the details. You can check it out if you want. Go on Google and search abiotic amino acids. And you'll see the abiotic amino acids, things like AIB and IVA, are amino acids that are common in meteorites, and they are not used in Earth biology. Then there's amino acids that are used only in Earth biology, like histidine. And then there's amino acids that are present in both, like alanine and serine. But in biology, they have left-handed only in the proteins, whereas in the meteorites, there's both left and right. So there's differences that can distinguish between meteoritic, which we expect to be on Mars, and biological, which is the question, are they on Mars? If you find them on Mars, you found evidence for life. If you show that they're not there, you've done due diligence in showing that the sample does not contain life using state-of-the-art approaches. And just to tease your scientific interest, not only will we be able to tell if there's no life, the abiotic case, let's go back to that, the abiotic case here, or the biotic case, life like Earth. Life like Earth is particularly dangerous. This is what you really want to show isn't there. The 20 amino acids used by life on Earth, homochirality, selecting for D, and distribution of certain distribution in the lipids, and so on. If you don't find that, and if you find abiotic, then you say, okay, no life. But from a science point of view, even more interesting would be finding an evidence for biological patterns, but not the pattern of Earth life. Now that would be, I think, more challenging in terms of Earth return. If the astronauts land on Mars and they take out their life detection, their little tricorder, and they say, well, folks, there are amino acids here, there are lipids, they do have a pattern they're not abiotic, but they're not the pattern of life on Earth, then they get to say the thing that everybody wants to say in astrobiology: it's life, Jim, but not as we know it. And then, are we going to let them come back to Earth? I would say no, but that's a question that we don't have to deal with yet. And here is a graphical representation of what I'm talking about. This is from a paper I did some years ago. A non-biological distribution of organics is flat. Biological distributions are not, they're selective. And an alien distribution would be selective and different. Okay, so this is sort of my wrap-up slide. If you want to be safe on Mars, we have to be able to search for life. Well, I didn't really dwell on this, but the obvious other use of life detection is astronaut health and safety. If there's something on Mars that's dangerous or allergic or an allergen or for some other reason annoying to the astronauts, you want to be able to measure it. And the instrument suite I showed you would be able to measure life forms and also measure molecules that might be a source of pathology or irritation to the astronauts. So astronaut health and safety. But astronaut health and safety is not a legal issue. That's purely a policy issue. If some company, SpaceZ, wants to send astronauts to Mars and their chances of surviving are low because of something toxic in the soil, or they're not going to worry about the perchlorate, they can. There's nothing that you can do to stop them. If the astronauts want to go and SpaceZ is willing to send them, then there's no standing to stop that. Bringing those astronauts home, though, violates the Outer Space Treaty, and everyone has standing because it's basically putting the Earth at risk. Okay, well, this is how a graphic summary of how you would collect those samples with a drill, and how you would look for these molecules, amino acids, lipid, and larger molecules. And again, the emphasis is if you detect only meteoritic amino acids and lipids, that is adequate evidence of biological safety. It also shows that your instruments worked. Okay, I want to move off a little bit, something that often comes up, and it may come up in your discussions. Once you send humans to Mars, you have ruined the chance to search for life there. There's a lot of astrobiologists that say that once you send humans to Mars, there's no point anymore in searching for Martian life because humans will contaminate the whole planet. I think that's bonkers. The view that human exploration will permanently ruin all life search on Mars has no basis in field work. We send humans to Antarctica to search for life. We send humans to the Atacama Desert to search for life in these very Mars-like environments. And we know how to do it cleanly, and we know how to do it without contaminating our samples. We know how to recognize life that's not contamination, and we know how to recognize life that is contamination. I don't understand why this is considered a problem. Furthermore, humans and the drilling infrastructure they could bring would greatly help the search for life. In fact, my opinion is we're never going to do the search for life on Mars properly until we send humans. And the way to prepare for it is field studies on Earth, especially deep drilling, provide insight on how to do aseptic drilling on Mars. And I point to a particular study that we did in Antarctica, led by Peter Doran, where we were drilling into an ice-covered lake that had never been exposed. And so they drilled in a way that the drill, as it went down into the ice, drilling down, was sterilized on its way down so that we did not contaminate the lake. We know how to do, humans know how to do things cleanly and search for life without contaminating it. And that's the end of my formal presentation. I'm hoping that I had enough time, or was fast enough, that there's time for questions, Nicole. So I'm going to stop sharing if I can figure out how to do that.
Yes, there is time for questions.
Great.
Absolutely. Mohammed Sheikha has raised their hand. Please go ahead.
Thank you a lot, Mrs. Nicole, and thank you, Mr. Chris. I'm Mohammed Sheikh. I'm from Syria, from a smart school team, smart Sarai school team. And I have a question, Mr. Chris, please. And thanks a lot for this brilliant informations about the amino acids that would be under. The best question is, what are the possibilities of continuing to produce the deriving energy inside the missile? And what is the time period to do all of these stages? Can we test that with any software?
Well,
And thanks a
it's
lot.
it's possible to produce fuel on Mars, rocket fuel on Mars. So you can produce the fuel for a rocket on Mars, but it does take time and energy. Those calculations have been done. You can find them in papers. I'm sure Nicole can find those references. A lot of them are associated with the Mars Society. In fact, a lot of those studies.
Yes, yes, we can help. You will be assigned mentors. We'll talk about that later. That can also
Great.
help things. Nawar.
My name is Nawar Karam. I'm from Syria, and I'm also from Saraya Smart School team. My question is about, do you think that genetic modification will play a role in agriculture on Mars, and like methods like CRISPR-Cas9 or other methods? And if you think so, what traits should we focus on editing the most? Is it salt stress tolerance, thermotolerance, yield increment, or other features I haven't mentioned? And thank you.
That's a really good question, Stephen. I'll give you a two-part answer. One is I think that these new methods, as you discussed, like CRISPR, will be developed first on Earth. So I think what new approaches in agriculture will come on Earth, and then we'll take them to Mars. And on Mars, we will try to create the environment inside a greenhouse that's as Earth-like as possible, so that we can make most use of Earth-like agricultural technology. And I think that will work. There's one caveat to that, which was actually brought up by the last speaker, Stephen Kane, which is that you can't change the gravity. And so if it turns out that agriculture in 1/3 gravity, plants growing in 1/3 gravity, is not the same as plants growing in 1 gravity, then you have to modify the plants specifically for Mars. That's the only case in which I think you would do genetic engineering that's Mars specific on plants, is if the response to partial of 1/3 gravity was severe. And this is a point that often gets glanced over. People just assume that when we go to Mars, 1/3 gravity will be fine. Humans will be fine. We won't lose muscle and bone. We'll be able to come back to Earth. Humans living long-term on Mars will not speciate into a separate species. But we have zero data at 1/3 gravity. Well, virtually zero data. And so this is a big unknown. The first humans that go to Mars will be guinea pigs for life in partial gravity. We have data at lunar gravity. We have about a week of data, astronaut data, from Apollo. But we don't know if lunar gravity is okay too. And as was emphasized earlier in the Q&A as I got on, there's no way to change that. There is really no technology that can change gravity on Mars. We can block radiation, we can create pressure, we can create temperature, we can make an Earth-like atmosphere to every detail except gravity. So if there's a need to modify plants to grow in 1/3 gravity, step up with CRISPR and figure out how to do it. Just keep studying.
Now I'm having the technical difficulties.
It's one of those days, Nicole.
Yeah. I don't know. There's all kinds of stuff happening. Jacob, you're next. Do you have time for one more, Dr. McKay?
Yeah, one more would be fine.
Okay, Jacob, you're next.
Yeah, I was just wondering because as we're designing our mission to go look for life on Mars, there's lots of different possibilities for the forms of life that we can find, and a lot of the testing methods center around human-centered carbon-based life, which makes sense because that's the only life we've ever experienced and know how to test for. But do you think that there's any merit in looking for non-carbon-based life? And if so, like, what evidence would you look for? Do you think that that makes any sense to look for?
Yeah, that's a good question. very good question, but I'm going to split it into two parts. There's what you called human life, like life. I'm going to call it life as we know it. So all life on Earth is common, right? We have a common genetic code, common phylogenetic tree, and so on. So there's one life form on Earth. Let's call that life as we know it. It is carbon-based and water-based, but it's much more specific than that. You can imagine life not as we know it, that is still carbon-based and water-based. It's different in the details. It's different in, maybe it uses, let's take the most trivial case. It's called mirror life, where instead of using left-handed amino acids and right-handed sugars, it uses right-handed amino acids and left-handed sugars. It's just like Earth life, only mirror image. It is incompatible with Earth life. We can't eat them and they can't eat us, not easily at least. But it's still carbon-based, water-based life. So there's really two questions inside your question. The first question is, our methods for searching for life are usually very specific to life as we know it. If I take a sample and I take it to the lab and say, is there life in this sample? They're going to search for DNA. DNA, because all life on Earth has DNA. And they're going to search for other patterns like proteins and whatnot that are specific to life as we know it. What I'm trying to do in my presentation was generalize that and say, what are features of life, carbon-based life in water that are not specific to life as we know it? Because on Mars, the environment is likely to have been a water environment. Carbon is abundant, sunlight's available. So life on Mars, if it developed independently, is likely to be still carbon-based and water-based. That doesn't mean it's the same as life as we know it. And so we have to dig a little deeper and say, what could be the differences in carbon-based water-living life that's still carbon and water, but could be different in detail to life as we know it. A second part of your question is, what about life that's not carbon-based living in liquid water? The only place where we see a possibility for that is Titan. There we see lots of organic molecules, lots of carbon, but not water. The liquid there is liquid methane and liquid ethane. And so there we have our first chance of seeing life carbon-based, but not water-based. Beyond that, there's nothing in the books, nothing actionable. It's only science fiction.
Thank you, Dr. McKay, very much. I know for sake of time, you have to go. And there are several more questions. Professor Kane, would you like to answer one or two questions if you have time? If not, I will answer as many as I can.
Yeah, I can take a couple more questions.
Okay, Ruzgar.
Yes, hello. I've been actually wanting to ask what is exactly the limit of life and non-life. For example, if we have a primordial soup of something that could be life, does that still count as life even though it's not life, or do we just go have to multicellular territory?
That's a great question because nobody knows. That's the answer, right, Professor?
Yeah, I agree with that. I'm sure Chris would have some opinions on that, but yeah, I agree with you.
Yeah, we don't know. There is no actual perfect definition of life. Scientists cannot agree on when it begins, when it is life, or when it's chemistry. There's no real answer. No, there's no actual consensus, correct?
Right.
Yeah. Okay.
Let me ask this. If something can be life but is not life yet, does that count as life?
That
I would say no. And that's going to be difficult to diagnose. And this goes back to something I mentioned at the beginning of my presentation, which was about the anthropic biases, because when we start talking about things like that, if something is in the early stages of, say, Earth-based life, what were the processes that led up to life on Earth? And is there a pathway that we could imagine in, say, 10 million years, then it would mature into something which we would consider Earth-based life? Well, then that is then ignoring all the other pathways which may occur on other locations within the solar system or outside the solar system, many of which we are currently unaware of. And this ties back to what Nicole was saying about it. This is part of the problem, is like what is life? When we're looking for, say, biosignatures on an exoplanet, I'll often hear colleagues say, well, we don't know exactly what we're looking for, but we'll know when we see it. I actually disagree with that statement. I think much of the time we won't know it when we see it. We'll see evidence of life pass right before us, and we won't even recognize it. What you're asking is a fundamental challenge within this whole area that we're hoping to understand better.
Absolutely, I agree completely. Laksh asks, is there any perfect place that you feel that there is a very high possibility for life to be found on Mars, I presume?
For Mars, we're mostly looking at subsurface environments at this point, where it may have exist up until the present point. One thing I will stress when it comes to planetary habitability, as I said at the beginning, even though we're being anthropic about the topic, and by that we can fall into the trap of considering that Earth is somehow the epitome of life, but that's not true. Something I say to my students is that if you were teleported to a random location on Earth, then there is a very high chance that you would die. There's a 70% chance you would drown, first of all, and many other locations which are hostile for one reason or another. Either you would die from exposure or cold, or hypothermia, etc. And so when it comes to ideal habitable environments, that's something that I think a lot about. And it's certainly not true to say that the more water, the better, even though I spoke about water is fundamental. I mentioned at the very end about if Jupiter, for example, had delivered a lot more water to Earth, and such that there were no continents, would there be life on Earth now? It's an interesting question, because then you lose a lot of the important chemistry that occurs through erosion on continents, and the runoff that goes down into the oceans. And so it's actually a really interesting question about what would make Earth actually more habitable. Some of my colleagues refer to planets like that concept as super habitable. If we consider Earth habitable, then what would a super habitable planet look like? And I think it's a really interesting question.
I do too. We have time for one more question because I have another meeting I have to get to. Victoria. And anybody else, while Victoria's unmuting, if you want to ask these scientific questions, please email me and I will forward them the questions. Is that okay with you, Professor Kane?
Absolutely, yes.
Similar to the previous question, that's okay. With using the equipment that we normally look for amino acids, we use a different type of sensor or light detecting equipment to see microbes, organisms that we might not be able to identify.
I had trouble hearing the question, but I think that sounds like a question that should be forwarded to Chris, because I think it was to do with detection of amino acids.
Correct.
Yeah. I'm sure Chris would have a much better answer to that than I could provide.
Victoria, just please email me your question. It was very hard to hear you. Students, stay on because I have a couple of things to talk to you about. Professor Kane, thank you so very much. I appreciate your time again, as always. Please forward me any email questions to forward to the scientists who spoke today. And I have some stuff for you students to talk about real quick. So
thank you all, and enjoy the rest of the meeting. And happy to take any other questions. Bye-bye.
Bye. Thank you. Okay, students, I have had to reassemble some of the teams based on time zones and different situations. So if you are on this team here highlighted in blue, I have had to reorganize this team. If you are Katie, Lucas, Bingo, any of these people, Lisa, Abigail, Stephen, or Rahul, if any of you are here, please make sure to contact each other and check the document. The document is now read only, so please do not type on it or change anything. So this is the team for team 4. Also, I do not have email addresses for team 6 or 7. I'm going to put this, is anybody here from team 6 or 7? Just unmute and say you're here because there's two, I can't see everybody on the screen. Nobody's here from, none of these people are here.
I'm from team 6.
Okay. Can you, and all of these students, I believe, are associated together in the same school or something. Is that correct? 6 and 7? Hello?
Yeah, that's correct.
Okay. Can you guys,
Yeah, that's correct.
I'm gonna put this document in
Yes.
the chat. Can you please put your email address in it? So there goes the document. Please go to that document, make sure it's supposed to be editable. So we'll see in a minute if it is. Let me know if it's not. Also, come up with a team name for your team. Make sure it is simple, easy to spell, and easy to read. There are going to be scientists from different places reading your presentations, reading your papers. Make sure it's simple and easy. Sometimes students like to have very long, complicated names. It just makes it confusing for everybody. Simple and easy to read and easy to spell. I'm trying to get mentors for everyone to have a student or adult mentor to mentor your team because there are now 16 teams and I cannot mentor everybody. So you can connect with your teams on, so let's see. Ruzgar, you already have access to this document where all the teams are. So all of their email addresses are here. You can set up a Zoom link. Oh, I didn't share it. The team document where everybody's email, you can set up a Zoom, you can set up a Discord. You guys decide where you want to chat together. There's a lot of options to do that. Karun, did you have a question for me?
No, ma'am, my hand was raised from the earlier question. Sorry.
Okay. So here's the team document. This is where you can get your team's email addresses and contact each other. Some teams came in together, some teams have been rearranged. Oops, didn't want to do that. Okay. And let's see. Is this document which document? The teams? Somebody named A asked if the document was confirmed yet. The teams are pretty much confirmed. If you have a question you want to ask me privately, you can email me. Also, make sure you are always checking the syllabus every day. Tomorrow we only meet. It is not a requirement. If you have questions for me, we are just going to meet on the same Zoom link at this time here. For questions for me, if you want to collaborate with your team in a Zoom room, you can do that. We can work out any issues with the, teams or situations. I can answer questions. I am a Mars scientist, so I can answer questions about Mars as well. So tomorrow, 4 p.m. Pacific, 11 UTC, same Zoom link, not a requirement, only meet if you want to. And I suggest you meet with your team. Jeremy, yes.
I wanted to ask because I saw that the dates to present our presentations were on July, and me and my group have summer school during that time. We will be attending summer school, like all of my group. And so what will the dates be for, or like what will the times be for the presentations?
The time will be 10 a.m. Pacific, so 30 minutes before we met today.
Uh-huh.
But it's because we have 16 teams, it's going to be a very long day. So we may divide it up into 2 days. And if you guys can't make it, you can send a pre-recorded video. But
Okay.
in order to critique, you're gonna have to be able to watch all of the presentations in time to critique them on that Wednesday.
Okay. Okay.
Okay? So lots of planning. Okay, anything else? How can you put your email? You have to go to the link I put, the Google Doc, and it should let you type on it. If it doesn't, let me see. Okay, I had to update it. It keeps defaulting to viewer only. Noir?
I just asked for access to
Okay, I
editing
just
the
updated.
file. I'm not allowed currently.
I just
Thank you.
updated it. I just updated it. Yeah. The competition is on Zoom because we can't all expect you to fly to a local place, so it will be on Zoom. You will each, I might change it to 20 minutes per group just because there are so many groups this year, instead of 30, but we'll see how it goes. I will let you know. And it will be on Zoom. There will be mentors and judges watching as well. Do you mean tomorrow, Bilal? Tomorrow it is. Oh, that could be wrong. Let me look. Let me check. PM. It is PM. It's correct. So it's not a requirement tomorrow. Share the Teams document. I'm thinking making a Google chat. The Teams document is shared. You just can't write on it anymore. So you should have access. You should have access. And Ruzgar, I sent you all of your team members in the other chat. Go back and copy and paste it. I sent you all their emails.